Hi, everybody. Welcome to the Coastal Observing in Your Community webinar series hosted by Socorro. Socorro is hosting this webinar to celebrate our 10-year anniversary. The point of the series is to discuss and highlight coastal ocean observing in the Southeast U.S. Monthly invited speakers will discuss observing topics. Each webinar will be about 60 minutes and recorded and archived for future viewing. My name is Abby Wakely, Socorro's Communication Specialist, and I will be facilitating and moderating the webinar. All participants will be in listen-only mode. You can type questions for the presenter or technical questions in the bottom left-hand chat box. I will respond to them directly or post the questions to our presenter. We are recording this webinar today and will be posting the recording along with a PDF of the presentation on the Socorro website. We are very, very excited to welcome Dr. Ruing He today as our speaker. He is presenting on predicting marine physical-biogeochemical variability in the Gulf of Mexico and Southeastern U.S. shelf seas. Dr. He is a distinguished professor of North Carolina State University and an adjunct scientist of Woods Hole Oceanographic Institution. His research expertise spans from coastal circulation dynamics, air-sea interaction, to biophysical interactions. As the director of the Ocean Observing and Modeling Group, he conducts coastal ocean observations, remote sensing data analysis, and also leads the development of prediction models of ocean circulation, air-sea wave interactions, physical-biogeochemical couplings, as well as data assimilation. Dr. He, thank you so much for joining us. I'm going to go ahead and turn the controls over to you, which I think you already have, and you are good to go.
Great. Thanks so much, Abby. Can you hear me?
Yes, I can hear you just fine.
Wonderful. I put myself on a speakerphone. Well, thanks everyone for calling in. So I'd like to start by thanking Socorro for organizing this webinar series. We know this is a 10 years anniversary for IUs, and so I want to personally thank IUs for support researching my team. So I am a physical oceanographer by training, but over years I am quite fortunate to work with many colleagues on the coupling between ocean physics and the biogeochemistry processes. So I want to thank my team and also many colleagues listed down below. So what I'm going to do today is to essentially tell you about some of the latest model development we have been working on, looking to the coupling between physics and BGC, biogeochemistry. So I want to touch upon 4 different elements in model development. So the first one is on the coupled modeling. The second is on the two-way nesting. The third is on the ultra-high resolution wave modeling. And finally, briefly touch on the data simulation. And then I'm going to give 2 case studies. One is on the Gulf Stream meander, happened in the Southeast U.S. And the second one is on the Gulf of Mexico biogeochemistry studies in the Gulf. And then conclude with a summary slide. Okay, so let's jump into the first one. So the couple modeling. And again, we realized a few years ago that ocean is a very complex system that involves very important interactions among physics and biogeochemistry. So we have to look into a complete system. And also, although our focus is in the Gulf of Mexico and also South Atlantic Bight, we decided to build a model covers even larger domain. So this is a model that we have been working on, covers entire Northwest Atlantic Ocean. And the spatial resolution is about 7 kilometers. So we put lots of emphasis on getting all the major rivers into this system. And on top of these circulation models, we start to adding different important components. So the circulation has been simulated using a community ocean model called the ROMS. And We also add the wave component as well as the atmosphere, regional atmosphere prediction component. So this is handled by WRF model, and the wave simulation is handled by the SWAN model. So we are coupling 3 different community models. And then on top of the ocean circulation model, we also add the components like coupling to the marine ecosystem, the sediment transport, and very recently we also start working on adding the marine acoustic component. So by having all the different models start to talking to each other, we can better address marine environmental problem in our coastal ocean. So just briefly on the BGC, marine biogeochemistry. So we have been working quite closely with Kaja Fano to implement the Fano ecosystem model into the circulation. So essentially, the ecosystem model has both nitrogen cycle and carbon cycle with all the major BGC components processes considered. And as you can see that the model is able to handle phytoplankton, zooplankton, detritus, and on the carbon cycle component, we also start to, can simulate the DIC, dissolved inorganic carbon, and the PCO2. So we can look into the air-sea flux, carbon flux exchange, and also look into the particular organic carbon that exchange between the ocean and sediment. So all the major components are being handled by Kaja's Fano ecosystem model, and this is our starting point. So one thing we have done is to run the Northwest marine ecosystem model, environmental prediction model, in a real-time nowcast forecast fashion. So we call this system as a CNAP. So it's a coupled Northwest Atlantic Prediction System, CNAP. So this is a snapshot produced by our daily operations. So we are providing the sea level pressure and also wind prediction. This is coming from the coupled WRF model. And we're also producing predictions on the wave height. So color shading here is a significant wave height overlaid with wave direction. So this is from the coupled SWAN model. And then down here, we are showing the coupled ROMS model, ocean model predicted sea surface temperature, sea surface height in color, surface circulation currents in vectors, as well as sea surface salinity. Okay, so this is a suite of fully coupled environmental state variables that we're providing on a daily basis. So I want to just jump into what's going on now. So we heard from NPR this morning that we have 3 major storms now happening in the Northwest Atlantic Ocean. So Irma now is Category 5. We have another tropical storm, Katia, in the Gulf, and another storm, tropical storm, Jose, is coming to the west as well. So our model, CNAP model, covers this region, so we can now provide some information for both Irma and Katia. So I'm going to show you just quick results came from our today's operational simulation. So this is a forecast for tomorrow. So GMT, September 7th. So this is tomorrow, and this is the model predicted sea level pressure. So this is Irma, very low pressure system, and this is Katia in the Gulf of Mexico. Okay, so this is from the coupled WRF model. Showing here in the middle is a coupled wave model. So we have a very strong wave height associated with Irma, and also a strong wave height associated with Katia. And the vector here, again, a significant wave height direction. Okay, so down here on the right, this is a surface velocity. This is coming from the raw model prediction, coupled ocean model prediction, and showing 5 meters below the surface. So you can think about this as surface current. So not surprisingly, we have a very strong loop current and Gulf Stream. And in the Gulf of Maine, we have strong tidal currents. So the color shading here is the current speed vectors are showing the current direction. So focus on Hurricane Irma and the location for Hurricane Irma and also Tropical Storm Katia. We also see very strong inertial currents up to 1 meters per second. Okay, so this is the ocean response to the two very strong storms. And we know Irma is moving towards west, and it's going to be quite important to see its progressions in coming days. The National Hurricane Center says the storm is likely impact Florida, so my team will be paying very close attention on this storm. But this is the temperature. This is coming from the coupled ocean model predicted temperature for tomorrow. So as you can see, you see some cold wake. So the lower temperature, this is caused by Hurricane Irma. So the surface, there's strong upwelling, pulling the cold deep water up to the surface. That's why you have this cold wake signature. But if you see the water temperature west of Hurricane Irma is all very warm, so between 28 degrees to 30 degrees, so very warm water. And this is a warm body of water that can keep providing the energy, moisture to Hurricane Irma. So this is going to be a very strong storm. And again, we will have to be very careful and be prepared for this impact. So more information, people can go to this website to check on our real-time nowcast forecast for the ocean condition, marine environmental conditions for this entire region. So 2 weeks ago, we had the Hurricane Harvey. So we're also using the CNAP model to do some hindcast study on Hurricane Harvey, specifically on the precipitation and the wave height, wind speed, temperature, sea level. So again, this is a model simulated marine environmental conditions. I'm going to play this. This is animation, so let me play this so you can see the evolution. Give me 1 second. Okay. So this is from August 24th to 31. So you see this is a low pressure system moving along the west Gulf of Mexico and then made landfall in Texas. I have to play this one more time. And then this is corresponding sea surface temperature, wind speed, and that's precipitation. This is also one of others model predicted state variable called reflectivity. This is very similar to what we see from like Doppler radar observation. So we can compare this model state variable directly to Doppler radar reflectivity. And then correspondingly, this field is a significant wave height. So essentially, we are looking into detailed ocean response to Hurricane Harvey, looking into the precipitation. Specifically, we are very interested to understand the fate of all the fresh water on the land, how they can get into the ocean and their impact on the ocean circulation. So we are working on this problem right now. Okay, so let me move on to another features that we have been working on. So this is about two-way nesting. The CNAP model has about 7-kilometer resolution, so it's fairly coarse to some of the coastal applications. So we have a new research project started later last year, focusing on the circulations and frontal currents, the transport of North Carolina, so of Cape Hatteras. So the scale here is on the kilometer, so 1 to 2 kilometers. We are trying to understand the variability of the Hatteras front and its interaction with the Gulf streams, with the shelf mean flow, as well as with local wind forcing. So 7 kilometers is a bit too coarse. So one thing we've been developing is the so-called two-way nesting. So within the CNAP, we can have a multi-level nested domain. So we can have a North Carolina domain, and inside North Carolina domain, we can have a so-called Cape Hatteras domain. So typically, the downscale ratio is about 1 to 5. So in that case, you can go from 7 to about 1.4 kilometers, and then subsequently, you can go to about 300-meter resolution. Okay, so this two-way nesting capacity is quite exciting because not only the larger scale model is able to provide open boundary for the higher resolution child domain, the child model is also provide the high resolution information back to the larger scale. So there's a two-way feedback, give you a much complete ocean physics. So this is just a quick example showing what can we do now. So this is a 7-kilometer CNAP. This is a daily snapshot showing sea surface height and surface velocity. And then this is zooming into the North Carolina domain. Okay, so this is now it's 1.5 kilometers, so you can start to see much more detailed circulation features. So the color shading here, again, is the sea surface height, and the vector here is surface velocity. So you can start to see a very detailed circulation gyre, eddies, and frontal currents. And what we are working on right now is to have another higher resolution Cape Hatteras domain, which can bring us down to 300 meters. Okay, so the similar technology can be applied to other part of Sakura domain. So really depends on the requirement or scientific goal. We can use this two-way nested technology to other part of coast ocean, so we can downscale the CNAP and look into a more detailed coast ocean processes as we like, as user requirement needs. So move on to another features we're working on right now is so-called ultra high resolution wave modeling. So we're funded by Department of Energy to look into the East Coast wave energy resource. And to do this, we require a very high resolution wave modeling that can produce a long-term wave hindcast. So my team has been working very closely with Sandia National Lab to implement this East Coast wave models, and this is using the unstructured SWAN model. Again, this can provide a 200-meter resolution along the coast. And this is a few examples. This is in Georgia, and this is in East Coast Florida. So you can see the mesh, the great resolution. So very high resolution, 200 meters. And we have done extensive validations against all the NDBC buoy wave measurements. And we are working on a 31 years, this should be a wave hindcast for this entire East Coast. So covering from 1979 to 2009. So we are going to have 31 years wave hindcast for this entire East Coast region. And the idea is to use this long-term time series produced by this model to assess wave energy resource. And this can also be applied for other Sakura-related coastal projects. So we can look into the wave impact on the beach erosion, the coastline change, etc. So there's a suite of other potential applications can be supported using this long-term wave hindcast. And this is one example. So we also look into the storm impact on the wave. This is a snapshot of wave condition back in September 2005. We had a tropical storm Ophelia, and this is the impact of the wave. So the color shading is reversed. So the blue color actually indicates a very high significant wave height. So this is about 6 meters wave height, and the red color here is background color. Okay, so this is unconventional color scale that we are working to improve on. But again, this is a wave impact response to the storm, and using this high resolution wave model, we can start to provide much detailed information about storm impact, the wave build up right at the coast. A few words on data simulation. So as part of IU's effort and lots of PIs within Sakura as well are building this coast ocean observing system. So we are also working on data simulation that can make the linkage between the observations, a suite of observations with model predictions. The technology we've been using is called the 4-dimensional variational data simulation method. In conjunction, we also have this so-called adjunct sensitivity analysis that can be used to help design a observing system. So the model can help you to say which part in the domain is more sensitive to variability, and that can be the strategic location to implement more observations to provide more impact on the prediction. So the concept is quite similar, and details is in our publication. But the concept is we have observations coming from routine satellite observation, including sea surface height, sea surface temperature, and also in situ measurements of temperature salinity coming from buoys, from ship, from gliders, from floats, etc. And then you have a prediction model making forecast forward in time. And the model is driven for the regional scale model. The model is forced by the meteorological forcing, by the boundary condition, as well as initial condition. Okay, so you make a forecast using the model, and you can compare with observation. And there's always a model data misfit. And using the fold-var technology, we can use this model data misfit to drive the so-called Adjunct model backward in time. And this process will provide a refinement in the forcing, in the boundary condition, and initial condition. And then you can rerun the forecast forward in time. So this is an iterative process. And every time when you do this iteration, you are decreasing the model data misfit, and eventually that model is able to produce so-called the best possible ocean prediction. Okay, so this is the whole concept about fold-var, and we're in the process to implement this for Sakura and for the Gulf of Mexico, for Southeast Coast Ocean and as well as the Gulf of Mexico. So let me show you a few examples that we've been using this modeling two sets to help us understand the ocean processes, ocean environmental changes in the Southeast and the Gulf. So I'm going to start with a Gulf Stream meander example, and then I'll go to the Gulf of Mexico, show how we're doing with the Gulf of Mexico circulation and biogeochemistry studies. So for the Gulf Stream meander study, the key question we are trying to address here is how the Gulf Stream changes positions in the South Atlantic Bight. So this figure here shows 250 years ago when Benjamin Franklin first produced the Gulf Stream chart. So lots of people know he's a very famous, effective politician, but he's also a very accomplished oceanographer. So this is a map, his contribution in the Gulf Stream study. So shows if you drive your boat along the Gulf Stream, then you can move from Florida, North America to Europe much more quickly. So this is a mean position Benjamin Franklin drew 250 years ago, but we have a lot more observations now. So one thing we have been looking into is satellite altimetry. So in this study we used 13 years sea surface height observation from altimetry as a way to quantify the locations and variabilities of the Gulf Stream in the South Atlantic Bight. So the idea is we can use the sea surface height measurements, and we can compute the maximum sea surface height gradient. And using that gradient information, then we can quantify the daily cross-shelf distance of the Gulf Stream. Okay, so this is one example. So this is a daily snapshot of on May 28, 2009. And showing here in the thick gray line here, this is the Gulf Stream on that particular day. And this has happened to be the location of the maximum sea surface height gradient. Okay, so the Alvaso altimetry data give you sea surface height map, and then we compute sea surface height gradient, and then we can pinpoint location of this maximum gradient. And then what we did was to compute the cross-shelf distance between the Gulf Stream location and several key coastal stations. So Savannah, Charleston, Cape Fear, Cape Lookout, and Cape Hatteras. Okay, so we have from south to north, we have this cross-shelf distance every day for the last 13 years. Okay, so we are going to look at the time series of this cross-shelf distance as a way to quantify the cross-shelf of meanders of the Gulf Stream over the 13 years. And this is just repeat. So we are computing from south to north, 5 different transects. And I should mention that this solid black line here, so this is a mean Gulf Stream position we computed from the 13 years data. Okay, and the dashed black line here are 1 standard deviation, and the blue dashed line here are the envelope. So as you can see, the Gulf Stream at one point moved very further offshore. Okay, so this is actually the case we are going to study. Okay, so during this event, the Gulf Stream is about 70 to 90 kilometers further away from its mean location. So it has this very large meander offshore. This is a time series. So from section 1 to section 5, and you can look at their daily record. I'm sorry. Okay, so this is your daily record of the Gulf Stream cross-shelf location, and from 1993 to 2013. So the positive means the Gulf Stream moving further offshore. So the y-axis is the cross-shelf distance relative to the Gulf Stream mean position. Okay, and the negative value means the Gulf Stream move onshore. So you have closer to the coast, again, relative to its long-term mean position. So what I want to draw your attention is the Gulf Stream has a strong meander, strong deflection happen in start from November 2009 to about April 2010, to about March 2010. Okay, so during this time period, the Gulf Stream stayed further offshore, so it's about 70 to 90 kilometers further offshore relative to its mean position. And this deflection lasted about 5 to 6 months. Okay, and this is where this envelope is indicating. So for whatever reason, the Gulf Stream is staying very, very offshore. And Dr. Jen in my team and I, we had this paper in JGR talk about the reason for the Gulf Stream larger scale meander. So I'm not going to talk about the detailed physical processes, but this is coming from the model simulation we did for this paper. So essentially, you're looking at the Gulf Stream, a zoom-in view of the Gulf Stream in the South Atlantic Bight, and the color shading here, this is the so-called relative vorticity. Okay, so on the shoreward side of the Gulf Stream, you have positive vorticity, and on the seaward side of the Gulf Stream, you have negative vorticity. So you see the Gulf Stream is moving back and forth, and somewhere starting in September 10th, it start to have this offshore deflection. Okay, and this offshore deflection lasted for about 6 months, 5 to 6 months. In addition to the Gulf Stream meander, you also see lots of open ocean eddies, and this eddy propagate from open ocean to the South Atlantic Bight, and some of the eddies actually join into the Gulf Stream. So very quickly, the reason for this larger scale offshore deflection has contribution coming from upstream transport as well as the open ocean eddies. So let me just stop there without going into too much details. What I'd like to draw your attention is what's the response of the regional scale marine ecosystem to this larger scale Gulf Stream meander. We have some observations. So this is the data Jim Nelson from Skidaway Institute very kindly shared with us. So showing subsurface temperature condition and nutrient condition measured at this location. So this is right at the Gulf Stream edge in the South Atlantic Bight. Okay, so we have a temperature and the nutrients, and as a comparison, we also put the climatology, and this is from NODC regional climatology. So this is typical temperature subsurface profile, okay, and this is typical nutrient subsurface profile. So what we can see is during this larger scale Gulf Stream meander case, we had much colder temperature and higher nutrient content on the shelf. Okay, so what happened was, as the Gulf Stream moving offshore, it produced a very strong shelf break upwelling, and this upwelling is able to bring the deep, cold, and also nutrient-rich water onto the shelf. So that's why temperature is decreasing, but the nutrients content is increasing. That's due to this very strong shelf break upwelling induced by this large-scale Gulf Stream meander. And there's some other evidence. So this is coming from remote sensing. So if you look at the long-term mean sea surface temperature, so this is averaged from 2002 to 2013, and from November to March. So temperature and compare. So this is temperature and this is the chlorophyll. And compare with the temperature and chlorophyll ocean color for that 5 months. So November 2009 and March 2010, you can see that the temperature, the shelf-wide temperature is cooler during these 5 months compared to the corresponding long-term mean. And the chlorophyll is actually much higher. The shelf-wide chlorophyll is higher compared to the corresponding long-term mean. Okay, so the Gulf Stream is moving offshore. Water is colder on the shelf, and nutrients is higher. As a result, you also have larger primary production, so the chlorophyll is higher. So again, the Gulf Stream is impacting the shelf-wide ecosystem. So can we do this? Can we reproduce these processes using a couple of physical and biogeochemical models? So again, we are using this Kajafano's BGC model, has nutrients, nitrogen, and carbon cycling. So it has specific components for the nutrients. These are organic nitrogens, and there's phytoplankton, different site structures, phytoplankton and zooplankton. And the answer is yes. So this is a model simulated December mean condition for temperature, and this is December 2009 temperature condition. So the temperature shows it's cooler than the long-term mean average, and this is all from the model simulation. And then this is corresponding nutrient. So we see that we do have the elevated nutrient content also from the model simulation as well. Okay, so the coupled physical biogeochemical model is able to capture such ecosystem response to the Gulf Stream meander. So let me move to a few examples in the Gulf of Mexico. So in the Gulf, the focus here is on the marine ecosystem dynamics and on the carbon cycling. So we have a NASA-funded research looking into the carbon cycling and also the PCO2, the air-sea carbon flux exchange due to different ocean processes. So in this case, we're going to focus more on the carbon cycling. So a former postdoc, George Xue, he's now assistant professor at Louisiana State University, and us published a paper last year looking into the PCO2 seasonality. So this is a model simulated. So we coupled the ocean circulation model with the BGC model and come up with this so-called PCO2 water seasonality. So showing here, this is a PCO2 flux in the spring season, summer, autumn, and winter. So the model is able to come up with these spatial distributions and look into the temporal variations of the carbon cycling. In this case, we are focusing more on this component. But the entire subsurface carbon cycling and nutrient cycling are being handled by the coupled BGC model. So we had some observations. So we compared the model time series against in situ measurements for the Northern Gulf. This is Louisiana Shelf, and this is over the entire Gulf of Mexico. So historically, the communities has been working very hard to collect more carbon observations as a way to understand the ocean acidifications and how the climate change is going to impact the carbon cycles, the PCO2 budgets. and that allow us to look at the time series from the observation compared with the time series produced by the model. So overall, the model is able to capture the seasonalities, so that gives us some confidence to use this model to do a long-term projections about the carbon cycles, the pH values in the Gulf, as well as assess ocean acidifications in the face of warming climate. So working with Dr. Nick Shea of University of Miami, so Nick is deploying the subsurface drifters. So it's Apex drifter. The drifter not only measures the physical properties, Nick's drifter also has the biogeochemistry sensors. So it has the chlorophyll, has the dissolved oxygens, and that information can also provide extremely valuable data sets, subsurface data sets, to help us validate this Gulf-wide coupled modeling system. So we are working with Nick on this Montgomery-funded research to see how the loop current and the BGC response not only at the surface but also at the subsurface. So we will be reporting more results as next year or two as this project unfolds. This is another quite interesting processes happen in the Gulf of Mexico called the Green River. So Dr. Chuanming Hu of USF, he published a paper back in 2011 showing that there's elevated chlorophyll fluorescence at the middle shelf of West Florida Shelf. And so this is about 50 to 100 meter isobaths. And this elevated fluorescence coming all the way from Mississippi River Delta to the Florida Keys. And so this feature in his paper also has a lower temperature signatures. And there's other papers by Frank Muller-Carter's group and Bob Weisberger's group talk about the shelf circulation and green rivers. And so from the circulation perspective and also from remote sensing perspective, and we said that can we use the coupled physical and biogeochemical models to reproduce such features. So this is very preliminary, and we go back to run the model for December 2010 and compare with long-term hindcast, and we do see that similarly to what Chuanming showed in the remote sensing observation, we do have this river and tongue plume features in the surface chlorophyll, and you can see that especially in the difference between the December 2010 and long-term December mean. So you do have this elevated chlorophyll signature, as well as you see that's a cold temperature signature. So this is the temperature and comparison between December 10 temperature and the long-term mean sea surface temperature. So you do have this colder sea surface temperature signature. So it looks like the model is able to resolve this Green River feature, and we are in the process to understand the detailed physical and biogeochemical contributions leading to such features, leading the so-called the Green River formations in the Gulf. So again, we'll be reporting more results in coming months. So a few examples, and then I'd like to just share a few thoughts on path forward. So lots of things has been done in the last 10 years in terms of building coastal ocean observing systems and also developing more advanced numerical models. So lots of people talk about climate change impact on the coastal ocean because really this is where the society facing the most challenge. So we have to be in a position to be able to provide a better prediction, better observation to see how the coastal ocean is responding to all the variabilities. So the first point is I think we need to, still working very hard to better define the intrinsic, so-called intrinsic variability, to understand how our coastal ocean system respond not only to the synoptic forcing events like storms, but also how the system is responding to some low-frequency variations like seasonal changes, like interannual, interdecadal timescales. So this still require a long-term time series from observing system and long-term model hindcast. The second point is we need to emphasize on the strong coupling among the land, ocean, and atmosphere. So marine ecosystem, marine environmental condition is a multidisciplinary research topic, and we need to look into the coupling among physics, the biology, the geology, and the chemistry. They need to be fully quantified in a coupled sense. The new development in building a couple of physical biogeochemistry models in conjunction with a multi-scale nesting capacity can be a really powerful tool to help us to understand and forecast variabilities in our coastal ocean. And finally, on the data simulation, so we have to move we have to keep improving the deterministic modeling, the circulations and the BGC models. We also need to keep building the ocean observing infrastructures and then connect them using sophisticated data simulation technology like the 4D VAR system that we have been working on. So only through moving three different components, modeling, observation, and data simulation, we can improve the state of art of coastal oceanography and providing better understanding and predictions for coastal environment as a whole. So speaking of observation, just want to highlight some of observing efforts that we've been working on at NC State. So we've been working with Harvey and Catherine and Chad from UNC and Skidway and USF to build a coastal ocean glider observing system. So this is a few observation results from our glider efforts. So we are looking into subsurface temperature and salinity, and recently we also start looking to a survey along the Gulf Stream frontal location, so you can start to measure the subsurface, the Gulf Stream variation, and its impact on the shelf system. And another component is to look at the long-term remote sensing observations, especially on the sea surface temperature and the chlorophyll. So what happened in our region is because water is warmer, so lots of evaporations and the cloud formation. So typically we have lots of cloud coverage. So we are using a so-called the DynoEUF cloud-free analysis technology to remove all the clouds. So this has been done for the South Atlantic Bight. So this is an original observation with lots of cloud cover, and this is a cloud-free reconstruction for temperature and for the chlorophyll. So we have done this for both South Atlantic Bight and the Gulf of Mexico. So we have a long-term time records, cloud-free temperature and chlorophyll to help us look into the concurrent physical and biological response to different forcing conditions. So in summary, so we've been pushing on the prediction side of the coastal oceanography. So we have this so-called marine environmental hindcast and nowcast forecast system for the Northwest Atlantic Ocean that can provide a three-dimensional baroclinic ocean circulation prediction for temperature, salinity, velocity, and sea level. We also have a prediction for the wave, including wave height and wave direction. And also on the marine meteorology, we're providing hindcast, nowcast, and forecast on the surface wind field, sea level pressure, air temperature, etc. And the system is coupled with marine ecosystem model, so that's why we can also look into the marine nutrient, ammonia, phytoplankton concentration, zooplankton concentration, the total organic carbon, alkalinity, the PCO2, and also oxygen. So the hindcast go back to about 10 years. So since 2008 to present, we're also producing a nowcast forecast into the future. So there's also a few value-added products that if you go to our CNAP website that you can find out. So there's an online model skill assessment. We also develop user-defined functionalities, including virtual moorings, virtual transects, and also virtual drifter tracking, track trajectory simulation functions. We also in the process of preparing model ensemble and the data assimilative model prediction. And down the road, we're also thinking about working on the seasonal forecast and the regional downscaling about the different climate scenarios. On the observational side, we have a number of years of glider observed hydrography and working with fishery biologists to adding a passive acoustic sensing technology to the glider, so that can be used to perform a fish stock assessment. And for the remote sensing, we've been working on the cloud-free temperature and the ocean color reconstruction with a database all the way back to 2003. So hopefully all this information, observation, models, and the product can be used to help us to address important marine environmental issues that society is facing, including the ocean acidification, the fishery habitat, and hypoxia and harmful algal bloom. So again, I think we as oceanographers need to work closely together, not just one individual discipline, and only through working together we can better address multidisciplinary topic, and we can better serve our end user and scientific community. With that, I want to stop, and I will be happy to take any questions the audience might have. Thank you so much for your attention.
Thank you, Dr. He, for your presentation. We're going to go ahead and open it up for questions. I'm going to unmute everybody so people will have the opportunity to ask you questions directly.
The conference has been muted. The conference has been muted. The conference has been unmuted.
All right, so everyone should be unmuted, and if you have any questions, just go ahead and ask Dr. He. Fred, I see your hand is raised. I think you should be able to ask a question. You can also type your questions into the chat box if you're having a hard time or technical difficulties. Ruing, so Fred is asking if you have made maps of, is that SSS for Hurricane Harvey?
Yes, so we're working on that. So one of the challenges we are having now, Fred, is how to get this fresh water input into our ocean modeling. So in the past, we've been dealing with a point source approach. So we have a major river like Mississippi, Atchafalaya River into our circulation model through the point source approach. I think in this Hurricane Harvey example, extremely, a big area of land area flooded, and the water will all flow into the ocean. So instead of using the point source, we need to look into ways to add into the model using a so-called land source. And so that's a technical challenge. Another data challenge is we need to figure out exactly how much water got dumped onto the land and then flow into the ocean. So there are some remote sensing observation showing some fresh water signatures along the coast, but that remote sensing data is fairly coarse. So we're still in the process of get our hands on any observations we can get so we can better prescribe the fresh water along the Texas coastline so we can do a better job to predict the salinity distributions in the hindcast sense.
All right. So Fred has a follow-up question. He's wondering more about the track across the Gulf of Mexico.
more about the track across the Gulf of Mexico. So this is still on the Hurricane Harvey, right?
Correct.
Okay. So are you asking salinity's impact on the track forecast?
So what was that question for Fred again, Ruing? I'm sorry.
Yeah. So I was trying to understand what Fred is trying to ask. So are you asking? Okay. So he put this down. So asking about the impact of Hurricane Harvey on salinity, sea surface salinity as it passes over. We don't know yet. So we know Hurricane Harvey dumped lots of fresh water. So we will definitely see some low salinity signatures at the surface, extending from the Texas coast all the way to maybe mid-shelf. So we just have to do a better job to quantify the forcing, the freshwater forcing to the model, so we can do a better prediction for sea surface salinity. On the other hand, once you have fresh water into the ocean, that further stratifies the ocean. So I know in the past there's a study showing when you have a more stratified ocean as a result of freshwater input, that actually has the positive feedback to the storm. So I think more fundamental question is there any two-way feedback between the freshwater runoff and the intensity of a hurricane? So we don't know the answer yet, but I'm hoping that using the couple model, we can look into the detail, the two-way feedback process between the salinity and hurricane intensity.
All right. So I think you answered his question, and I'll put your email in the chat box so people can follow up with you directly. We have another question from Deborah Hernandez. She is asking, will your 30-year hindcast model runs be publicly available, and what is the schedule for completing that work?
Yeah, so Deborah, that's certainly the intention. So the project is funded by Sandia Lab of DOE, Department of Energy. So we still have 1 more year to go. So the simulation is being carried out right now on the supercomputers of the DOE, and the goal for the next several months is to complete all the simulations and write a report and publication. And by the end of the project, the goal is to make the 30 years wave hindcast database available. So we're about a year away from making the final closure of the project and make the data available.
Great, thanks.
And Jennifer Dorton is asking, Ruing, if you have worked with National Weather Service, National Hurricane Center, or other federal agencies to evaluate the models for operational use?
Right. So Jennifer, we've been talking to the NWS Newport. So I made a presentation some time ago to a Newport office. So at that point, we don't have a fully coupled system. So I need to go back to revisit them again. So last time I talked to them, I only showed the ocean circulation prediction capacity. But now we have a fully coupled system. I think NWS people would be interested. And we look forward to opportunity to collaborate with them more, because I think we have a mutual interest, and certainly if you can facilitate such an exchange, we'll be looking forward to that.
Great, thank you. And then Jennifer also has another question, and she wants to state that she's happy to help you work with National Weather Service, so we'll follow up on that. And her other question is, have you identified users for post-IRMA data sharing to identify effects of the storm on ocean chemistry and mixing?
So, well, Irma is not happening yet, right? So I think so far Irma is up and coming, so we have to run the nowcast forecast model to see what's going to happen. But afterwards, so we are, for any major storm, we are working on the hindcast. So we have a hurricane hindcast for Ivan, for Sandy. We'll be working on a hindcast for Hurricane Harvey, and certainly we'll be working on a hindcast for Irma. So we have a PhD student in our research team. So her research topic is on the BGC response to hurricane, and she actually just got a fellowship from NCC grant and space grant to address this very issue that you are raising, Jennifer. So I'm hoping that she can answer this question for you in a year or two time frame, because this is an overlooked question, how the BGC is going to respond to all the storms, and especially with all the major storms.
Thank you, Ruing. And Jennifer is following up saying, goal is to pre-identify groups that may want the data to show ecosystem impacts.
Yes, pre-identify groups. That's a great idea, yes. So if you have any suggestions about the potential group members, again, we love to talk to people and build up collaborations and share information.
Great. Are there any more questions? All right. Not seeing them typed in. So if we didn't get a chance to get to your question, please email Dr. He directly. I have sent you the email in the chat box. We welcome any feedback on the webinar series. And as I stated earlier, a recording of the webinar and a PDF of the slides will be available on the Socorro website, and that's socorro.org/webinar-series. The next webinar will be September 26th at 12 p.m. Eastern, and Ian Walsh from OTG Hydromet will be joining us, and more information will be provided in a couple of weeks. Thank you all so much, and Ruing, thanks again. I really appreciate you joining us for this webinar series.
Well, thanks everyone, and we'll be in touch.
Thank you. Have a great day.
Okay, bye-bye.